through topic by topic. Today we're going to have a look at trying to determine the rate of a reaction and then try to work out the rate determining step. So let's have a look at a problem. Unfortunately, a lot of these things seem to be really maths, so whether you like maths or not, as a chemist you end up having to do some. So if we have a look at a particular question. Right, I've got a reaction, and this reaction's all about taking a alkyl chloride. So we've got some sort of alkane with a chlorine attached to it, and we're reacting it with sodium hydroxide. And we perform a whole series of experiments. Here they are, 1, 2, 3, 4 and 5. What we do is we change the concentration of the chloride. This is our first experiment by having here simply a basic number, whatever it's going to be. This is our concentration, 0.05. It's one I've made up, with 0.1 of hydroxide, and what I've got then is some sort of measurement of the initial rate, and I've decided that's going to be 4. Bear in mind this is not a real experiment, this is one that I've made up. Moles per decimeter cubed per second. In a second experiment I have doubled the amount of the first chemical but kept the other one the same, and what we see is that the rate has gone up from 4 to 8. It's actually doubled. I repeated the same experiment. This time we have tripled the amount of the chloride, keeping the hydroxide the same, and here we can see that this is now tripled. Looking at the first experiment and the fourth experiment, I've kept the amount of chloride the same, but in fact I've doubled here the hydroxide, and we see that this rate has also doubled. And then, for a bit of fun, we've doubled the amount of chloride in the fifth experiment, and we've also doubled the hydroxide, and we see that the rate has now quadrupled, 4 to 16 times 10 to the minus 4. We write that out as 1.6 times 10 to the minus 3. So there is a simple reaction. So what can we say about this reaction? So a typical question might ask you here to do something like deduce the order of the reaction, and we're going to do it first with my chloride, and then we'll do it with hydroxide ion. So we're seeing here that this rate here, by doubling the concentration, we've doubled the rate of the reaction. So we call this here a first order. To remind you, if we've got a 0 order reaction, then if we changed the rate, this is going to be the rate this time, and this is going to be my concentration of whatever I've got, it would have no effect. So by putting more or less in, it's not going to affect the rate of the reaction. If we look at a first order reaction, then still with this as rate and concentration of A, we're going to see a straight line relationship, and indeed that's what we're seeing here. If this is our baseline with here the normal rate of reaction. Then if I double this, that's doubling. If I triple this, this is tripling. So our graph is going to look like this. So we're working out the order of reaction, and indeed it's that one. An other option might have been that if we've got the same reaction but it's perhaps doing something like this, and again this is rate and concentration, then this is going to be a second order reaction. So we've got 0 order, we've got a first order and a second order, and this clearly is a first order reaction. If we're trying to do this with comparing this time the OH concentration, then if we look at our experiment, I have kept this the same, but I've doubled the concentration of the hydroxide, and we're seeing a double of the rate of reaction. So for this one, we can say that this is also first order. If you're asked why, then simply this answer is the same as that one, that if we double the concentration, then we have doubled the rate. If we look at the final version here, from here I have doubled this concentration, I have doubled that, and so we've actually quadrupled the rate of the reaction. So we can work out the rates of our reactions simply from looking at this rate equation and the details that we've got here. So if we're now asked to work out what the rate is for this reaction, then I can say that the rate is going to equal some constant, which I don't know what it is, and I'm going to give it the letter K, and it's going to be the concentration of my chloride, and it's going to be times by the rate of my hydroxide. What else could they ask us in here? Well, could they ask us to calculate the rate constant for this reaction? So let's calculate the rate constant. We've got it here, but it's in the wrong format. So I need to change this round. So by bringing this round, I'll take those underneath basically. So K is now going to equal the rate divided by the concentration of my RCH2Cl times by my rate for my OH. Now I might have my rate constant here for something, so I've got that determined. Up here I've got my rate, which is 4 times 10 to the minus 4. So if we put that in, 4 times 10 to the minus 4, all over my concentration, which is going to be here 0.05 times 10 to the minus 3 minus, yeah, it's just going to be that, isn't it? I don't have a number, and that one is going to be again 0.1, then we can work out what this is. So all we have to do is hop over to the calculator, and we've got our equation, which is going to be 4, and I'll put it as a fraction. So I've got 4 times 10 to the power of minus 4 all over my 0.05 times 0.1, and this will give me my answer, which is 0.08. The units we need to work out, so the units for the top one, I'll just put this above here, the units for the top one were moles, decimeters minus 3, seconds to the minus 1, and that is over the other ones, which were going to be moles and dm cubed times moles dm cubed. Well, they're going to these are going to cancel out, and those will cancel out, which is going to leave me with mole minus 1, because it's underneath, decimeter cubed, which is here, would be underneath, so it'd be, and technically it'd be negative, so that's going to be per decimeter cube, so it's going to be, when we go up the top, it's going to be positive, and seconds to the minus 1. So there are my units. Now, the next part of this sort of equation might ask us something a little bit horrible to try and work out. And a typical question would ask, now, once you've done this, can you perhaps work out for me the actual mechanism for this reaction? So let's have a look at what's going on in this reaction. So if I've got this simple reaction, I've got to have a look at what's happening, and to look at what's happening, we're going to take my chemical, which is going to be, make sure you can see it, R, C, I've got my 2 H's and my Cl, and this we're going to add some hydroxide to. So let's bring in my hydroxide ion. Now this hydroxide ion is going to react with this, and eventually we're going to form, right over on the other side of the paper, plus Cl minus. So there's my equation. This is, however, a reaction which is a first order reaction, and it's dependent on two different things, so two different things have got to happen. So we're looking at this probably coming in, attacking the carbon, and we'll remember that the electrons here are going to be coming out of there onto the Cl. So I think we're going to get some sort of intermediate, and it's likely that our intermediate is going to be something like this. where this bond here and this bond here are actually going to be sort of temporary. They're doing something, and so this is going in and that's going out, but in the meantime, in the middle, there is going to be this thing existing, and that's going to give me here an idea of this reaction. And so this is going to be an SN2 reaction. So we can work out something about a reaction simply based on data that we might be given. And by looking at these experiments, looking at the concentration changes, looking at the rates, we can see that this reaction is going to change. And so we can determine here some things about the rate of the reaction. Let's have a look at another one of these and let's see what we can have. So let's take another reaction, which I'm going to take here, something like some nitrous oxide, and I didn't really want to put the arrow in there because I want to put some oxygen in there. Let's react this with some oxygen. And this is going to give me 2 NO2. All of these are going to be gas, so nitrogen monoxide plus oxygen going to give me nitrogen dioxide. Right, so we've got our experiments that we're going to put in. We're probably going to do a few different experiments, and we'd look at the initial concentration of my NO, and let's sit this one at 1 times 10 to the minus 3, and we'll start off with some oxygen, and we'll also give this 1 times 10 to the minus 3, and we've got some sort of rate here, and let's imagine that's going to be 6 times 10 to the minus 4. Just making these numbers up. So let's try doubling the amount of NO, and we'll leave the amount of oxygen the same, and let's imagine this rate here is now going to have increased, and I'm going to make it increase by 4 times. So this is going to be 2.4 times 10 to the minus 3. And let's try this one again. We could perhaps triple this concentration, leaving this one again, and this time we're going to have it, if it's gone up here by 4 times, then this is going to go up by 8 times, so we'll have 4.8 times 10 to the minus 3. So I think that'll be right, and never helps when I'm making questions up. Let's then simply be awkward. Let's double both. And if I double both, then we'll think of a number I can put in here. And we could put in, I don't know, I don't know, something like that. Let's see if we can work out what's going on. Let's compare experiment 1 with experiment 2. And we've doubled the amount of NO whilst we've left the amount of oxygen the same. And we can see here the rate has quadrupled. This suggests that the rate here for making our NO here is simply going to be proportional to this squared. May not have got this number right, I was just thinking about that. Right, so if this is sort of proportional, that's confirmed by looking at experiment 3, where this now should technically treble, I think, shouldn't it? So that's trebled. So that's going to be not right. So I didn't get my numbers right when I was trying to think about it, but this is also going to treble. Okay, so that would not be, here it's going to quadruple, here we're going to have it increasing here by the square, and this will be increasing by the cube. So we've got this rate trebling. Now let's have a look at the other one. Let's have a look at what's happening to the oxygen concentration. Now if we know what this one is doing, this one is doubling, then what's happening to the other one? So here the rate's increased 9-fold. So if I work out here, we've got then this, so the rate triples on that one, so the rate is that, and the rate is proportional to my oxygen squaring. No, it's not square, it's just to the 1. Right, okay, so my rate therefore could be proportional to my concentration of my NO and my oxygen. Perhaps I should have planned that one out rather than just trying to make up some numbers. So the rate constant is relatively easy to try and work out. Then we can just rearrange the equation trying to work out what actually goes on. We can look at the effect of concentration. We can also look at the effect of temperature on the rate of a reaction, and the rate of the reaction can be changed by temperature in exactly the same way. Now why does this actually happen? Well, we need to look at a special curve for this, which is Boltzmann's curve. And this is probably where my son panics and says, I didn't say I was going to do that. But if we look at a typical curve, it's going to look something like that. And what we're going to do is we're going to have the energy of activation, and I'm going to shove that in here. This is my activation energy. We've got energy along the bottom, and this is the amount of particles with the energy. So this is, if you like, the fraction of particles with this amount of energy. And as we change the temperature, so this is perhaps going to push this further along, it's going to be lower down, and this is a very badly drawn graph, will go along there. And if I increase the temperature even more, so we find this is temperature 1, temperature 2, temperature 3, so more molecules will have that energy. So the shape of the graph changes with temperature. As the temperature increases, a greater proportion of molecules have enough energy to react. And this is the main reason for the increase in the rate of reaction with temperature. So hopefully they're not too difficult to have a go at doing, especially if you get the right numbers. Now let's have a look at how we would actually determine the rate determining step. What do we actually need to do to try and do this? So let's have a little look and see what we can see. So the rate determining step. Let's suppose I've got some chemicals in a reaction, and I'm going to have A plus B plus C, and this is going to give me my two new chemicals, which are going to be X plus Y. This reaction might occur with the following steps. Maybe A plus B react first in a fast reaction to make D. Now D is something that doesn't appear in the final reaction, so it's just a intermediate. And maybe D will then perhaps here react with, I don't know, give me E. This is a slow reaction, and it's going to give me a second intermediate. And then we discover that E reacts with C to give me X and Y. And this is a fast reaction. So step 2 is the slowest step, and this determines the rate. As soon as any D is made, it will start making E, but this reaction can't continue until E is made. So it doesn't matter how fast this reaction goes, everything can be turned into D instantly, but E can't react with C until E is actually made, and this is the slow part of the reaction. So the reaction will always move at the rate of the slowest step. So if I want to look at the rate equation for this, the rate equation is going to be equal to my concentration of A, B and C. Now let's look at a reaction that might actually do this. And so we're going to look at the reaction of iodine and acetone, or propanone as you would call it. So let's take some propanone. Not doing well today. And I'm going to react that with some iodine. And what's this going to do? Well, this is going to quite happily shove an iodine in here. Like that. Plus we're going to get some HI given off. So this is here iodopropanone. Now if we look at what the rate expression here is going to be, then we can say that the rate here is going to be equal to some constant times the concentration of my acetone, propanone, and perhaps some acid. So let's try and work out what might happen. So let's start off with what we've got, my acetone, and we're going to have a slow reaction. And what's going to happen here? My hydrogen is going to bond here. This is going to make this very slightly positive. And then what's going to happen? Well, this stuff is now going to give me a fast reaction, and that's going to give me perhaps an intermediate. Like that. We're going to add the iodine, and this could be a fast reaction. And what we're going to do is put the iodine across here. And then finally we'll have another fast reaction, and doesn't really matter where I put the eye on here. We get that. So in this case we can see simply that in this rate equation the hydrogen is the slow step. And it doesn't matter how much iodine I actually put in, it's not going to alter the rate of this reaction. So this is why this reaction is going to be zero order in relationship to the iodine, because it's not going to appear in the rate equation. Can we do this the other way round? Can we try to determine the rate determining step? And the answer is yeah, I suppose we can try and determine the rate determining step here. And let's do something like the hydrolysis of something like an alkane to try and work out what's going on. So let's take a haloalkane. Let's take here CH3 let's take a tertiary one, and let's add some hydroxide to this, and this is going to give me and we're told in this case that the rate is equal to the concentration of this stuff, CH3 3 CBr. So let's see what we do know. The rate equation here basically shows us that the rate determining step here involves only one molecule of the tertiary alkane. The amount of hydroxide here has absolutely no effect on the rate of the reaction. So we can work out that that must be involved in the fast part of the reaction. So let's make a guess at what's going to happen. We've got CH3 Br, there's three of those, and that we have decided is going to be a slow reaction. Something's going to happen, and then step 2, what's going to happen is we're going to add the OH, and this is going to be a fast reaction, and we know what the overall reaction is going to be. I've got to start with my CH3 3 CBr plus my OH, and that's going to give me this plus my Br minus. So I know my overall equation, so what we've got to try and do is to work out what we've got. So step 1 has got to somehow form here an intermediate. and we know that this intermediate is totally used up by the OH to give us our reaction. So, writing this out again, I've got my CH3 Br gives me, with a slow reaction, our intermediate, and then we know that our intermediate reacts with the OH minus in a fast reaction to give us so if this is our reaction, so what we've got to do is work out, well, what could this intermediate be? And since it's only this thing, then I'm guessing something is going to happen. Perhaps, remember, if you get this wrong, you get as many marks as if you get it right, as long as you make up something that's going to be a suitable intermediate. So let's draw our steps in. I'm guessing that our CH3 CBr with a nice slow reaction is going to give me CH3C, we'll give it a plus, plus a Br minus. So that's my guess at an intermediate. It may be right or it may be wrong. It doesn't matter, because this intermediate then is going to react with my OH minus, and that is going to give me a fast reaction, which is going to give me my CH3 OH plus my Br. So here we've got a two-stage mechanism. This substance that I've made does not appear in the final reaction, in the final things that we make. So this may or may not be right, but it basically doesn't matter, because in a question, as long as you make this intermediate and then you use up this intermediate, then everything works really well. So that is trying to work out the rate determining step. And I've tried to give you here some ideas about how you might go about trying to do this sort of thing, trying to work out how to solve something. I hope you found that useful. That's a fairly quick thing, but it's important to go through and have a go at quite a lot of these. If you found this useful, give us a thumbs up, and if it's really useful and you find all these helpful, then please subscribe, and I will see you next week on some more A-level chemistry, topic by topic, when we'll start looking at equilibria. Until then, stay safe and take care. Bye bye.